This video explains how to use Farfield 2 to create a rigid pavement design, which we will develop on a stabilized base using an aircraft traffic mix that includes aircraft with complex gear geometry. This video is part of the Farfield Pavement Design series by the Federal Aviation Administration Office of Airports. Refer to Advisory Circular AC 150/5320-6, Airport Pavement Design and Evaluation, and AC 150/5335-5, Standardized Method of Reporting Pavement Strength, PCR, for the basis of the design and evaluation procedures implemented in Farfield. Topics include Farfield Rigid Pavement Design, Traffic with Complex Gear Geometry. Step 1. Name the job and section. For this video, we will open an existing job, Farfield Video, and add a new section named Rigid. Step 2. Set the starting structure as New Rigid by clicking the Pavement Type dropdown and selecting New Rigid. This creates a starting structure with 4 layers: P501 PCC Surface, P401/403 HMA Stabilized, and P209 Crushed Aggregate on a subgrade layer with a modulus of 15,000 K 172.4. In the starting rigid structure are 2 columns added only in a rigid analysis. One is the design strength R of the PCC surface, and the other is for K, subgrade stiffness. The design strength R represents the in-service flexural strength of the concrete. This is different from the strength used in construction specifications, which is a contractual acceptance strength, generally the strength at 28 days. See AC 150/5320-6, Chapter 3, and AC 150/5370-10, Standard Specifications for Construction of Airports, Item P501, for additional information on concrete strength. The user can edit R to be between 500 and 1000 psi. Typically, this is set at 650 psi or less. For our example, we will set R at 650 psi. The other column is for K, subgrade stiffness. As with flexible design, Farfield uses modulus E in the design analysis. The user can enter the subgrade stiffness either as modulus or K. Conversion from K to E is defined in AC 150/5320-6. Step 3. Edit the structure to reflect site conditions. For a rigid structure, Farfield requires a minimum of 3 layers and a maximum of 5. See AC 150/5320-6, Chapter 3, for requirements and recommendations for rigid pavement. In this example, adjust E, the subgrade modulus, to 7,500 psi. Step 4. Add traffic. In this example, let's use a stored aircraft traffic mix, CS Cargo. If you plan to reuse this traffic mix, create it in Farfield, then save the aircraft traffic mix to a file. The CS Cargo traffic mix is similar to the traffic mix at an airport with significant cargo traffic. It includes traffic from 177,500 pounds to over 1 million pounds. Aircraft with complex landing gears, such as the Boeing 747 or A380, are treated as 2 aircraft by Farfield, one for the main landing gear and one for the belly landing gear. Selecting the gear tab in the main window and then selecting the 747-8F shows the main gear geometry, and selecting the 747-8F belly shows the belly gear geometry. These aircraft are linked for weight and activity, such that when entering departures and adjusting weight, you'll only need to enter it one time on either the main or belly gear. When performing the structural analysis, Farfield analyzes the impact of the main and belly gears separately. Step 5. Run the thickness analysis by clicking the Run button. Prior to running the thickness analysis, Farfield checks for minimum layer thicknesses of underlying layers. In a rigid analysis, Farfield uses the horizontal stress at the bottom of the concrete panel as the predictor of the pavement structural life. The maximum horizontal stress for design is determined by considering both edge and interior loading conditions. Farfield uses a 3D finite element model to compute these stresses. The solution time for a rigid analysis depends upon many factors, including the number of aircraft and the number of different gear types. In general, a rigid design analysis takes longer than a flexible analysis. A rigid analysis may take several minutes to complete. The analysis is complete once Farfield adjusts the structure to achieve a CDF of 1. The recommended structure is 18.7-inch P501 PCC surface, 5-inch P401 HMA stabilized, and 6-inch P209 crushed aggregate on a subgrade with a modulus of 7,500 psi. A review of the traffic and the CDF graph indicates that 3 gears contributed to the total damage: the 747 main gear, the 777, and the A340 main gear. Last, you would typically adjust the layer thickness to up to the closest 1/2 inch and run a life/compaction analysis. This evaluates the to-be constructed structure for life and subgrade compaction requirements. See video, Flexible Pavement Design, General Aviation for discussion of compaction requirements. In this example, adjust the P501 PCC surface thickness to 19 inches. Review the section report and save as a PDF for inclusion in the project's engineer's report. In this example, we identified how Farfield treats complex aircraft with main and belly gears. We also discussed design strength versus contractual strength of PCC and performed a rigid analysis. See other Farfield videos for examples of other pavement types and for more information on traffic, user-defined aircraft, and pavement classification ratings. See AC 150/5320-6 for additional information regarding FAA standards for pavement design. See AC 150/5370-10 for information regarding FAA recommendations for material specifications. Please visit www.faa.gov/airports to find these documents, this tool, and other related design tools. For additional information, contact the FAA's Office of Airports. The FAA appreciates your interest. Safe landing.